Hey yo, what's up guys? So today we're going to talk about deviation from ionic bonding. It's quite a good topic that I would like to talk about comparing to atomic spectra, which I'm shit at, but anyway, yeah. So yeah, let's reintroduce actually what is ionic bonding to start off with. It's a basic concept that we all need to have. We all learned that in GCSE, and it's so simple that we can literally talk about it inside out with our eyes closed. So anyway, let's talk about it. What is ionic bonding? It is basically the electrostatic force of attraction between oppositely charged ions. So, the perfect example is sodium chloride, NaCl. So, as we all know, I'm just going to draw the outer electrons. We have a sodium with 1 electron outside, and a chlorine atom with 7 electrons outside. Well, one day, chlorine was like, oh god, I want to be neon, I want to be argon, I want to be a noble gas. And sodium was like, yeah, me too. So what they did was, sodium gave and transferred the electron to chlorine. And they made what we know as an ion, which we have a sodium cation and a chloride cation. I'm not going to, an ion. I'm not even going to draw the electrons here because it's quite not relevant anyway. So after that, they have a good friendship because they were like, oh god, we are both now noble gases, we are both happy. So they formed a good relationship and they formed a bond, which this is all we know as a ionic bond. So this is like the basic story of ionic bonding. And yet we know that, oh, it's a sodium and a chloride that happily lived ever after. But this is actually not the case. In the reality world, what happens is rather that they have a perfect sphere, that as we know that they have a perfect sphere because we assume that they are perfect, the true reality is, as we know that chlorine is way larger than sodium, so we're going to draw it on scale, it's basically that. So the sphere that we usually draw represents the electron cloud. And as we can see here, the reality world that shows us is how there's a distortion in the electron cloud of the chloride ion. So scientists, they found this out. I don't know how, and I don't know why, and I don't even want to know. They wanted to know why this distortion happened, rather than thinking of a perfect theoretical situation. And so they came up with 2 new ideas that we need to learn. The first one is polarizing power. That is for cations only. And the second one is polarizability, which is for anions. So I'll quickly define what the 2 terms are, and I'll talk about it in a simpler way, in a way that we'll all understand. So polarizing power is the ability to polarize an anion by distorting the electron cloud. I mean, it's quite a long definition that you need to learn, but once you understand it, it's way easier. Anyway, so that electrons are attracted to cation, causing the bond to assume some degree of covalency. So this is polarizing power, and for polarizability, it is the tendency to become distorted. Well, one's passive and one's active. To become distorted by a cation, so that, which is basically the same as here, and I'm not gonna copy that because it's just a waste of time. But from these two definitions that we have, we can then conclude that, so what actually sodium ion does is, we know that after going back to the story, after that sodium has become a cation and chloride has become an anion, sodium is a bit greedy and he was like, oh god, I want my electron back, because now that we need to draw the electrons. And sodium was like, oh god, I want my electron back, I miss him, something like that, yeah. And since he has a positive charge and chlorine has a negative charge, and we know that they both attract each other because positive attracts negative, sodium would try to attract the electron back to itself. Try to. And what it does is it sort of like it distorts the whole sphere thing and the circle thing here, which then causes what we know as the distortion of the electron cloud here. This big thing right here. So this actually brings in some covalency, as we have here in our definition. So what that means is, let's say that one day you became a chemist and Mr. Sharp or Miss Jones told you to burn some sodium chloride until they melt. And so they gave you a theoretical value of 900. Oh, this is a theoretical value that I made up myself. So it might not be true, it might not be accurate one, but anyway. But then you did the experiment and you did actually burn sodium chloride. If you have a really, really good heat source, and you found out that the value that you obtained is actually 930 kilojoules per mole. And you were like, oh my god, Mr. Sharp or Miss Jones is wrong. What is wrong with them? It is actually that it is due to the fact that there's a slight covalency in the bond of sodium chloride. So even though we know that they are a ionic bond, there's actually some covalency here. And this covalency is present in all ionic bonds. And this is what we mean by the deviation from the perfect ionic bonding. It is the phenomenon of polarizing power of the cation and the polarizability of the anion. So now that we know the two main things here, we need to then further discuss. So how do we distinguish the different strengths of polarizing power and polarizability? So there's two main factors that affect this. So two factors. Well, the first factor is the charge. And the second factor is the ionic radius. And we both know that, and we know that these two factors, they join together to form something called charge density, which is equivalent to the charge over the ionic radius. So let's dig deep and look at cation first. So for cation, you would, for good polarizing power, for very, very good polarizing power, you would want to have a very, very high charge and a very, very low ionic radius. So let's give us an example. Lithium cation and potassium cation. So which one has a high charge density? Well, it's obviously lithium. Where is the reason behind? Well, it's really because of the fact that they both have single positive charge, and that we know lithium is way smaller than potassium. So the ionic radius of the lithium is way smaller than potassium. So that's why lithium has a high charge density and a higher tendency to distort the electron cloud of an ion. So if you think it in another way, think of the positive charge being spread out in the atom or in the ion. So as we can see here, obviously, lithium has a smaller surface area for the charge to be spread out. So we can say that it's more concentrated as in the positive charge. So that's why the polarizing power, the ability to distort the electron cloud, the strength of the positive charge is way stronger than potassium. Well, I'm sure that you learned about the fact and the theory of charge density somewhere in chemistry in A-level, but I'm just here trying to reinforce it because it's quite useful. Anyway, back to an ion, which we're going to discuss the polarizability to be distorted, the passive one, God. So considering the charge, we would want the charge to be very high, obviously. If you have a high charge, so that you could attract each other more easily. And the second thing is, for the ionic radius, you would actually want it to be high as well, to be distorted. Well, think about it. Perhaps it may make sense in some way. So you have a fluoride ion. You have an iodide ion. So which one do you think is going to be distorted more easily? Well, in some way, people think that it's going to be fluoride because obviously it's the fact that fluoride has the same charge as iodide, and fluoride has a smaller ionic radius, so the charge density is higher, etc., etc. Well, it is in some way, but it's ultimately the ability to lose the electron. To lose the electron to the cation, to have your electron cloud distorted, and that's what we mean here. So as we know that in iodide it has more electron shells, so the outer electron is further away from the nucleus comparing to fluoride ion, and as a result, we can conclude that for iodide ion, its outer electron can be easily distorted or easily attracted to others compared to fluoride. And this is what we mean by polarizability here. So it's slightly different for polarizing power and polarizability here. These are another concept that you need to understand. And last but not least, I would like to finish off with a simple question that comes up frequently during exams. So they give you a scenario where they were like, oh, a student has discovered aluminium trifluoride and aluminium trichloride. And they realized from their teacher that this aluminium trifluoride is actually ionic and 8LCO3 is actually covalent. Explain. Well, you can try and do that yourself. To pause the video, and I'll talk about the answers later. Right, so we'll now talk about the reason behind why this is so. It is really to apply the knowledge that you have just now about polarizing power and polarizability. Well, so as we know that aluminium, they have the same cation, and FYI, aluminium's quite a strong polarizing power agent because it has a +3 charge and has a very small ionic radius. So its charge density is quite small, it's quite large, and it can easily attract the electrons from an ion. So it's really the fact to compare between fluoride and chloride. Well, they have the same charge, negative charge, single. So I'll put the 1 here. But who has a larger ionic radius? Well, it's obviously chloride, yes? So as a result, the chloride ion has a higher polarized ability, and that means that its electron cloud could be more easily distorted. So if we draw a diagram in some way, so I'll just draw one aluminium ion and one fluoride ion. We can then convert it into something like this, as in the reality world. So we can see that there's quite a lot of distortion here, but they're not quite yet merged together, because as we know that for ionic bonding, there must be a gap. It's like a must be a gap. If there's no gap and there's an overlap of the circle or the electron cloud, so overlap, it becomes covalent. So in aluminium chloride, it is really something like that. What I'm trying to emphasize here is that the electron clouds nearly touch, or they touched, or they're trying to overlap. So this is why we call aluminum chloride as a covalent character. So 50% ionic and 50% covalent. And this is the reason why, because chloride has a higher polarizability. So just to finish off, I'd like you to understand that yes, there is such fact of an ionic bond being a covalent bond in some way, having some degree of covalency. But at the end of the day, the basis of ionic bonding is really the electrostatic force between opposite charges. It is really this. That is the basis of ionic bonding. And the distortion bit is really some weird phenomenon that happened in the natural world. And scientists are trying to find a way to explain this. And they came up with these two different explanations, polarizing power and polarizability. So this is the end of the video. And I'll make another video on deviation from covalent bonding next. So peace out.